Hello again, this is Galen Pickett, Cal State University Long Beach, Physics 151. Today I want to talk about Section 13 of Chapter 3. So, this is collisions, and I have a collision at right angles here to analyze. So the system consists of, so there's an intersection here, and I've got a car going at the speed limit towards the intersection, and I've got a truck going at the speed limit towards the intersection. The system is these two objects here, so I'll just draw a system boundary around those two. Now, they're going to blow right through the intersection, and they will collide, and the combined object is going to go off. There's still the system is going to go off with some velocity I do not know yet that I'm going to call v final. So the wreck will have some velocity v final. This is situation A. Situation B is I have a car going at the speed limit to the east, and I've got a car that's going at twice the speed limit to the north. These things still collide, so here is the system before the collision, and here's what the system is after the collision, and I'd like to know how fast each of these things are going. Which of these situations, A or B, is the object going faster? So let's just analyze these things from the point of view of the momentum principle. As far as the collision is concerned, it's not that there are no forces from the surroundings, it's just that the forces from the surroundings are usually much smaller than the forces that happen inside the system. So from just before the collision to just after the collision, we can consider them to be isolated systems, so that from the momentum principle point of view, the initial momentum of the system is equal to the final momentum of the system. The momentum doesn't change because it's just the forces inside the system which are acting, and those forces can't change the total momentum of the system. So let's see what this means for this collision. I've got two objects. The initial momentum of the system, let's say this is my x direction and that's my y direction. I can write it as two vectors, one for the car heading east, that would be m v0 in the x direction, nothing in the y and nothing in the z. And then I add to that the momentum of the truck heading north. That's it's 0 in the x direction, and the y direction, it is 2m v0. That's because it's got twice the mass of a car, but it's heading at the speed limit, and 0 in the z direction. So the initial momentum is m v0, 2m v0, and 0. Now, because of the momentum principle, I know that the final momentum of the system is going to be the same thing, because the momentum of the system did not change in the collision. M v0, 2m v0, and 0. So that's what the analysis of the momentum principle tells us for situation A. Let's see what it looks like for situation B. For situation B, I have my initial momentum. Again, I've got something that has got just an x component momentum and something that's just a y component. So I'll write those two vectors together. In the x direction, I have m v0, and then 0 from this one, and 0 for z for this one. In the y direction, I have m, but now times 2v0. So I've got one car having at a velocity 2v0 and 0 in the z direction. Again, because of the collision, the final momentum is going to be equal to the initial momentum, which is m v0 and 2m v0, 0. And we now have the situation where the final momentum in system A and the final momentum in system B are exactly the same thing. You can see this momentum is the same as that one. This momentum is the same as this one. And therefore, the initial momentum in situation A is the same as the initial momentum in situation B, and therefore their final momentum are the same. But I'm asking about what is the final velocity. I want to know how fast these objects are going, and these systems have got different masses. In situation A, I've got an object of mass 3m going with this momentum. Here I've got an object of 2m going with this momentum. So P final is the mass of the system times V final. Here I've got P final is the mass of the system times V final. So V final is 1 over 2, and I'll just divide out the m, v0, 2v0, 0. And here I'll have v final is equal to 1/3 v0, 2v0, 0. So even though they got the same momentum, this one is going faster. And you can imagine what would happen in objects with different masses, but the same momentum, have got much different velocities. The small object has got a much bigger velocity. You can imagine what would happen on the 605 freeway if I've got a car with a mass of 1,000 kilograms and a truck with a mass 10 times as great. Let's say it's a car carrier of 10,000 kilograms. If these two objects had the same speed, so they're both going the speed limit, say 65 miles an hour, 65 miles an hour, the truck has, P truck, has 10 times the momentum of the car, even though they got the same velocities, because it's got 10 times the mass. If instead I put a momentum limit, instead of a speed limit, a momentum limit on the 605, and I make that momentum limit be P max is equal to 1,000 kilograms times 65 miles per hour, then the car is perfectly happy. The car has got a mass of 1,000 kilograms, its maximum velocity, it's going 65 miles an hour, so V max for the car is going to be this momentum limit, 1,000 kilograms times 65 miles per hour, divided by the mass of the car, which is 65 miles an hour. Great. So the car is able to go at its normal speed. For the truck, well, its maximum momentum is still 1,000 kilograms times 65 miles per hour. Divide that by the mass of the truck to find out what is Vmax of the truck. So that's 1,000 kilograms times 65 miles per hour, and divide by 10,000 kilograms. Kilograms cancel, 1,000 and 1,000s cancel, so I get 6.5 miles per hour. If we have a momentum limit on the 605 freeway, the cars can go 65 miles an hour and the trucks can go 6.5 miles an hour. And that's really to get at the difference between momentum and velocity. In the original collision here, these two systems had the same momentum, but this one has got more velocity.